Welcome to the CERIAS seminar for March 27th, 2019. Today we're honored to have with us Professor Wei Zhang, who comes to us from the University of Missouri, Columbia. Dr. Zhang is an expert in secure multi-party computation and particularly techniques for making this practical in the real world, dating back to his dissertation, which looked at problems in kind of the real world requirements for secure multi-party computation to be to actually be useful and solve real problems, as opposed to some of the kind of either went overboard on what people needed for security or didn't go far enough. Professor Zhang has a distinguished career. He's recently joined the University of Missouri at Columbia, having spent several years at Missouri Institute of Science and Technology. But before that, he did his undergraduate work at University of Iowa. His graduate work was done right here at Purdue. As a CERIAS student, this is where you could end up. He was affiliated with CERIAS and active in CERIAS when he was here. And so we're really excited and pleased to have him back and joining us. So I will turn it over to Wei, who will be talking about some new things that are happening that he is developing in secure computation.
Thank you, Professor Clifton, for the introduction, and I'm very happy to be home again. So I think this is a great place. I have really profound memory about Purdue, so it's always appreciate the opportunity to be back to share some of the work we are doing at the moment. So so the main topic gonna be secure multi-party computation. In particular, we want to talk about some of the how to design more efficient secure comparison techniques, right? So that's the main topic. If you have any question, you can stop me any moment, right? And so I can clarify any question you may have. Just a quick question here. Anyone, do you have some background in secure multi-party computation? Anyone here has something? Right. So if not, that's okay. Some of the details may be a little bit too much, but hopefully I can give you some general idea regarding what is secure multi-party computation. What are the main concepts, definitions underlying the SMC concept. Okay, so so here's the motivation regarding why I'm doing secure comparison. So many organizations, right, they want to outsource data, right, to a cloud. For example, in this example here, the healthcare organization can outsource the medical data to the cloud, right? Then the cloud can do data analytics and then send the result back to whoever querying the data. So, but the problem by doing this, there are a couple challenges here. One, the data may contain sensitive information. Right, so especially for medical data, and then another thing, the cloud cannot be fully trusted, right? Because there's some insider threat, right? So unhappy employee can grab the encryption key, get the data sell to other parties. Another one, a security breach can happen, right? So they can the intruder can get the data, so to violate privacy, right? So. So because this problem, we need to, have a solution that can protect the sensitivity or the privacy, of the medical data or personal data. So how do we protect the privacy? So these are some of the common techniques out there. I'm not saying common. The first one definitely not common, right? So the ideal solution, right? The ideal solution is where, we have a trusted third party, right? If you trust someone completely, and then the data can send to that organization, that party, the party can analyze it and then get the result back, right? This is so-called the ideal solution, right? Why it's called ideal? Because under this model, you can maximize the data protection, right? That's why it's called the ideal. but may not be, I mean, I don't think it's practical, because how are you going to find someone, everybody can trust, right? So another solution, kind of like data, perturbation technique, right? You can perturb the data so that the server, won't learn the sensitive information, but maybe at the same time, some of the statistical information can still be preserved, and the cloud can still apply or analyze data, for the organization, who need the results. Another technique called searchable encryption, right? So you transform data in a certain way such that the data can still be searched by the cloud and get you the result outcome. The next one is called the fully homomorphic encryption. So the basic idea is that you can encrypt the data, and then on top of the encrypted data, you can do addition, multiplication, without ever decrypting the data. So if you can perform, these two operators, right, addition and multiplication, then you can perform any operation, purely based on the encrypted data, right? So the cloud don't even need to see the real data, original data, so to fully protect the security of the data. The last one I listed here is called the secure multi-party computation, right? And so the goal of the secure multi-party computation, right, is actually to accomplish the same outcome, as if there were a trusted third party. So basically, we can develop SMC, or secure multi-party computation protocol, to replace the need of a trusted third party. Okay, that's the goal of SMC. Okay, so please, you can stop me anytime if you have any questions. So what's the problem of SMC? One problem is the generic solution is not very efficient. By generic, I mean the garbled circuit approach. So I will point that out a little bit later, give you a little bit more detail on that. And then the big data become even bigger, right? And so the scalability, is become worse and worse due to the large amount of data we have. Another problem is the SMC requires at least 2 or 3 independent servers, right? Sometimes it may be hard to find even one server, right? So now we need to find like 2 or 3 servers. So that could become a challenging problem. So our goal here, the main problem here is the efficiency. We want to somehow to improve the computation efficiency, right? How do we do that? Many of the data analytical tasks based on comparison, right? So think about the k-nearest neighbor queries, right? The range queries, right? The similarity computation, right? So all these are based on comparison operator. So the efficiency of the comparison, the secure comparison, can affect the efficiency of more advanced SMC protocol. So that's the reason, if we can somehow, right, improve the efficiency of SMC, the comparison, and then hopefully we can increase the efficiency of more advanced protocol, right? That's the goal here. So that's one of the reasons why we are looking at the comparison protocol in particular. All right, so here's our contribution of our current work, right? So we want to develop highly efficient SMC comparison protocols. Right, so what do we mean by comparison? Right, that's easy. Right, you have 2 numbers, let's say A and B. You want to return, 1 means A is greater than B, and 0 otherwise. Right, so this is a very normal, standard, comparison operator. So, how do we achieve the efficiency we need compared to the existing solution? Right, we combine, several, strategies. Right, the first one, we are using additive, secret sharing, right? The traditional technique, they use the Samir secret sharing, right? Samir secret sharing is based on the polynomial. It's a little bit computationally intensive. So additive secret sharing is very easy and simple to compute. Another idea we use is called the, protocol, asymmetry, right? So many of the existing work, the protocol is symmetric among all the parties. Everybody doing the same thing based on their shares. So I will give you one example a little bit later. Another one, another technique we use is called the dynamic, group switching, for different, share sizes. So why we want to switch different groups? The reason being, in group of, if the value in the group of 0 and 1, So all the computation in that group can be done locally, between, among these parties, right? So we want to maximize the computation in the group of so-called Z2. So Z2 means, 0 and 1, right? So again, more example will come. So by doing that, we are able to decrease the order of the complexity, as well as the magnitude of the dominating, term coefficient, right? So we'll share some of the outcome we have, at the end of the protocol. Okay, so here's the overview of our design. And so this is the rest of the talk. And so I'll give you some background and then talk about the design of our protocol. And then I will highlight some of the future and the research direction. So any question you have so far? Or can you hear me well? Yes.
The last thing you said, basically you're saying you're both reducing the degree of the polynomial and the constant factor in your complexity.
So I'm reducing like the order of the complexity. Like order means like from n cube to like n power 2, right? That's kind of reducing the order and coefficient. Sometimes under the big O notation, they hide the coefficient, right? Like the big O n sometimes could be big O 1,000 times n. So we reduce the 1,000 by, for example, could be instead of 1,000 can be 100. So that's what I mean by reducing the coefficient as well. I'm not sure if I answered. Okay. So we try to reduce both, but hopefully we got the job done. All right, so some background, right? So when we design secure protocols, like under the SMC setting, first thing we have to understand what is the adversary model. So by adversary model, we mean the behavior, for among the participating parties, right? So in the SMC protocol, all the SMC protocol require several participating parties, right? So they need to communicate, they need to collaborate to perform, some of the computations, right? So their behavior directly determines, what kind of security guarantee we have. So among all the adversary models, the most common one is called the semi-honest, right? What that means is that, every party who participates in the computation, they follow, the steps required by the protocol, right? So if I have a secure comparison protocol, the protocol gonna tell, the party, let's say Alice and Bob, right? So the protocol gonna say, Alice, you do the folding computation. And then the protocol gonna say, Bob, you do the folding computation, right? So if Alice and Bob are semi-honest, they're gonna follow whatever the protocol, informs them to do. Okay, that's called the, semi-honest. Another one called the malicious. Malicious means like the party can behave in any way, right? So they can refuse to participate, right? So if we ask them, okay, so to execute my protocol, but they can refuse, right? I don't want to do that, right? So that's a part of the behavior under the malicious model. So anything, so they can behave arbitrarily to compromise the security, right? That's called the malicious adversary model. Another one called the covert. So covert means, malicious behavior can be detected, right? You don't have to prevent them from happening, but this can be protected. I mean, can be detected, right? If you run, some of the verification protocol, right, to do that. You probably can tell, right? So the protocol secure under the semi-honest model is generally more efficient because you're assuming they can behave, according to the protocol, right? So you don't have to prevent them from, diverge from the normal execution of the protocol. So the protocol secure under the malicious model can be very expensive because you have to add additional computation to force the party to follow the protocol. Right, so I'm not going, give you the details, but just some kind of intuition behind why the protocols, can be very efficient under the semi-honest model. So to prove security, right? How do we prove security for SMC protocols? We generally compare the protocol you developed, right, to the ideal solution, right? I mentioned about the ideal solution where everybody trusts party, right? The trusted third party, right? And give the party the information, then the party can analyze everything for us, right? For comparison, right? The Edison Bob can give their number to a trusted party. The party can compare and then send the outcome back to Edison Bob, right? So this is the ideal solution. So if we design a secure comparison protocol, we need to analyze the information leakage between the two model, right? So the real model, the ideal model. The real model is the one, where you execute your own protocol, right? You develop a new protocol, you're executing that. So in this picture here, the real model, everybody is sending the message, right? So this message is sent required by the protocol. So if we can analyze the information leakage between these two models the same, and then we say the protocol you develop is really secure. Okay, so how do we say they are the same? Depend on the computational model. So one, if they are computationally indistinguishable, you can say the same, right? If the adversary has a limited computing power, right? If the adversary doesn't, they have unlimited computing power, then to prove they are the same, you have to say, they are, uniformly, random, right? So these two execution, they are purely random. So you cannot really tell difference regardless how much computing power they have. So here is just an example. The bad guy, the adversary cannot tell the information leakage between the two, and then we say the protocol under the real model, the one you design, is really secure. Right. So what are the approaches, right? Under SMC, the building blocks. And one of the building block is the Gauss, garbled circuit, right? So I mentioned about the comparison. Actually, the comparison problem is also the one introduced by Gauss, famous millionaire problem. I don't know if you read that paper. And so the two millionaires, right, want to learn who's richer, but they don't want each other to know how much money they have. So that's kind of like the secure comparison protocol can get a job done. So this is the first classic example to motivate the secure multi-party computation, right? So in his paper, he suggested, the garbled, circuit approach. So this approach is, so early on I said about the generic solution, it's not very efficient. So the garbled circuit is considered to be a generic solution, right? So the technique here is that we know how to evaluate the AND gate or the XOR gate, any logical gate, security, right? If we can do that, we can evaluate any, garbled circuit, any circuit, right? Boolean circuit security. So any polynomial function can be represented by a Boolean circuit. So that's why you can evaluate any function security, right? This is called the generic solution. But this solution is not very efficient, still. Okay, generally speaking, right, it's not very efficient, but they are efficient for smaller input size, right? The smaller input size give you a reasonable size circuit, right? If you have large data, then the circuit become, intractable, the size. Another solution called the homomorphic encryption, right? This one is different from the fully homomorphic encryption, right? I mentioned about the fully homomorphic, but this one is only, most times people use additive, homomorphic encryption, right? By Pallier as an example. But this one, the communication cost is very high. Reason being, if you want to encrypt one single bit, for example, right? So one bit of data, you have to use a key size of let's say 2048 bits to ensure the security. So after the encryption, your data size become 2,000 times more than before, right? So clearly, you pay the overhead, that's kind of too much, depending on the size of the data you have. So another approach called the secret sharing, right? So secret sharing doesn't have the problem of the homomorphic encryption. You can, if the data is 1 bit, you could share with the same size. You can generate 2 random bits to represent, one single bit, right? You just double the size instead of, 2,000 times more than, the original data size, right? But here, the secret sharing has a problem of, requiring at least 3 parties, right? You need to have 3 parties to do all the computation. I can mention, I will tell you a little bit more just a little bit later. And then another problem is the rounds of communication, right? So if you use secret sharing, then most often you have a number of rounds you have to go through to finish the computation, right? So many of the research, even for comparison protocol, secure comparison protocol, currently people look at how do we design a comparison protocol, with constant round communication, right? So the more round we have, the more errors, right? The network, problem can play into a picture, right? You really want to reduce the number of round of communication, right? Establishing communication, can be a expensive, operation as well. Okay, so that's why the goal we want to use the secret sharing, but without the complexity of the secret sharing, right? So we want to design something is a constant round, the comparison protocol as a constant round comparison protocol, and more efficient than the existing solution, right? That's our goal here. Okay, so a little bit more information regarding the secret sharing schemes. The schemes we can use need to have the following following, right? The first one, in the scheme, we can give a value x, right? We can share the value using the scheme. For example, given a value 10, right? So under the additive secret sharing, right? If the domain size is 100, right? So for example, the domain of maybe over ages, right? From 0 to 99. I don't know what's the oldest person. Anyone knows who's the oldest? What's the age for the oldest person? 124 or something, I forget. But the range, let's say 200. That's probably enough to cover everybody, right? The oldest person. So if we want to share the age 10 in the group, in the domain of from 0 to 200, for example, what should we do? We just initially we can select a random number, right, in the group from 0 to 200, and then we can do we can use the 200 minus the 10. I had to make sure I got everything right. So basically, the 10 is equal to what's the first number we select? Do you want to give me a number? So we need to select a random number in the group first, right? That's the first secret. Can you give me a number? Can you give me a number? 25. Okay, so 25 is good. So we can have 25 as the first secret, right? It's randomly selected, and then 25, plus another share. We need to have two shares, right? Second share give us mod. The group size now is 201, right? Give us 10. So now you can derive what's the value for the second share, right? So that's called the secret sharing, right? You select one random value from the group, and then you can derive the second share by using that formula. Okay, and so each share alone is kind of uniformly distributed, right? So that's why they are secure. So that's the idea. So you need to have something you can share the value, and you can also need to based on the number of shares you have, you can also reveal the original values, right? That's called the reveal. And you have the addition. Addition means you can add a number together without knowing the real number, right? So you have two values, A and B, right? So A and B are shared. How are you going to produce the share of A plus B, right? So the secret sharing scheme allow you to do the addition without communicating, between the two parties, right? So if the shares belong to the two parties, as above, each one has a share of A and B, they can get a share of A plus B locally by adding their own share together, right? So that can be done locally. Another one, multiplication by a constant. So if you have, let's say Addis Ababa again, they have a share of A, right? They don't know the value A, but they have a shares of A, right? Using the example I gave you earlier. And how do they compute given a constant value, right? Multiply with A. Okay, how to do that? So this can be done. The scheme allow us to do that locally. Okay, so there's no communication here, but they have to share the constant at the first place. If you consider that as a communication, that's fine. But most often, this value has already been pre-shared, right? Most often they don't count as a communication. So all these operations can be done locally, by the individual parties. What is missing here, right? So if we want to solve any computation, right? So this operator is not enough, right? So which operator is missing from this list here? Multiplication, right, of two shared values. So here we have addition, right? So you have two shared value A and B. You can compute the shares of A plus B, right? But here, this scheme doesn't have a multiplication. You cannot do let's say you have shares of A and B, you cannot do shares of A times B locally, right? So that's why people develop different protocols to enable the multiplication, right, between the two shares. All right. So how to do that? I mean, there are many. There are some classical papers, to depend on how the share is constructed, right? Under Samir, you can do one way. Under the ATC sharing, you do it differently. Okay. So, but we can do that, with some kind of communication. So one design issue here to minimize communication, we don't want to use secure multiplication, right? As many, we want to reduce that, as much as we could, to hopefully we can minimize the communication, right? So that's the idea. One of the design ideas we have. All right. So this is the protocol. Many of the existing work, based upon, right? So this is the first protocol, for the constant run, right? Constant run secure comparison based on secure sharing, designed by Dangard. He's one well-known person in cryptography literature. So what's the? I will go through this one, and then I can show you, our protocol how it differs, from their design. So in this protocol, the input, right? The input is the two shared value, right? We have the A and B. The notation here, like A0P, bracket, means A0, right? That's the 0th bit of the input value. Is a secret shared in the domain defined by P, right? So P is a modulus, right? The example I give you about the age, I use the modulus like 201, right? So here we is a general, variable, right? P, and then B is also, shared similarly. And so the output is a C, the bracket. Generally speaking, the bracket C means the C is shared. The C represents the original value. The bracket C represents the share value. The P there, the subscript, means the group size, right? So where the value, the share came from. So if we C equal to 1, then we can say, A, A is greater than B, and 0, otherwise, right? So this is the input, output, right? How do we do this computation, right? So here the steps involved. So how do we do comparison, in general, right? So think about the comparison at the bit level, right? If you have two numbers, right, A and B, how can I tell, right? So let's say A is bigger than B. So what's the first step, in general? Don't worry about security, right? Don't worry about that. Just in general, at the bit level, right? If we want to compare two numbers, what kind of operation you want to do? So the first thing we need to know is the, which bit location, right? So one thing, the goal there, right? The ultimate goal is that we want to locate, right? So the most significant bit location where the two numbers are differ, right? So the first, right? The first most significant, significant bit location, right? How do we identify that? To identify that location, we need to do an XOR first, right? So to answer the two number, and the XOR gives us the locations, right, where two bits are different, right? Now we need to locate where's the first location. Once we got the first location, we can go to either A or B, right? If we go to A, if the A, that location is 1, the B is 1, which means A is bigger than B, right? Does it make sense, everyone? So if we go to B, right, if B is 1, B is bigger, B is 0, B is smaller, right? But you get the point, right? So the most important the most important information we need to find is really the most significant location where the two values differ, right? So how do we identify that? The first step, we need to compute the XOR operation, right? The XOR operation, again, all these operations here can be done securely. I'm not going to give you the detail how to do securely because this involves lots of information. I don't think we have the time to discuss that, but just assume, right? To understand the concept, you don't know the detail. You don't need to understand the detail, but let's assume the XOR operator here can be done securely, right? So the first step, we apply the XOR operation to find all the locations, right, where the bits are different, right, between the two values A and B. So the next location, let me show you the example here, right? So here we have an example like the A and B here, right, in the binary representation. So after the SR operator there, I don't have a pointer to pointing you. Maybe I can use my mouse here, right? So this line here, you do SR, then the E becomes 0, 1, 0, 1, 0. Again, here I show you the regional value, but when you execute the protocol, right, the parties don't know the E value at all, right? So this protocol here is executed by 3 parties, right? So each party gonna do the same thing here with their own share, right? So each party, what I mean by same thing, same means they perform the same computation, but based on their individual shares, right? So I have 3 parties. 3 parties can execute this XOR operation, and the input is the share values, right? So they don't know anything about A and B, right? At the end, what they have is the share of the E value, right? Again, they don't know anything about E, but they only know the shares of the E, okay? So everything is still secure. The next operation, this one is called the pre-OR operation, right? So this operation gonna produce this value F here, right? So this F here, the first value is 0. So the first one, right, for the E, so that's the most significant location where the 2 values are different, right? In my example here, right? So after that location, this value F here, everything become 1, okay? So if you do this operation, right? Again, I ignoring all the details about how do you gonna perform this pre-OR operation, securely. But let's assume we can do that securely, right? So at the end, this is the value for F. Then another thing we're gonna do is this, G vector, right? In this vector, the other value are 0, only one value is 1, right? So that value indicating, right? So the most significant bit location where 2 values are different, right? So this vector is very important. After we got this vector here, the G vector, you can multiply G with A here, right? You do a multiplication, bitwise multiplication, right? So once you do the multiplication, you can retrieve. I think I need to update, this example here. I think I made some changes, but actually this H here, you need to have 1 here. When you multiply G, right? So G multiply with A here, what you got? You got 1, right? So this location here is 1, then the other location is 0. If you sum them together, you got a value 1, right? So 1 indicating A is greater than B, right? So that's the idea. Does it make sense? I know I'm kind of ignoring lots of details, but I'd like to give you some high-level, understanding about this protocol here. Again, this is a typo here. I made some changes to my examples, but I didn't update this value H here. This H here, the second location here, need to be 1 instead of 0. So it should be 0, 1, 0, 0. Okay, and then if you combine all the shares together, then you should get 1. Right, again, here, at this moment, right, everything is bitwise shared, right? To finish the computation, you want to make sure you won't have 1 share for the whole number, H. So this is what you got here. You want to have 1 share for the value for H. Okay, so that share in our example here is 1, meaning A is greater than B. So I will go a little bit faster. So let me talk about our design. So you saw this one, right? So this one is executed by every party. So that's why I mentioned at the beginning the protocol, the existing protocol are symmetric, right? Because everybody doing the same thing based on their own share. The only thing different is their own share, all right? So we're gonna break this symmetry to improve the efficiency of the protocol. Right, so here is the over design of the protocol overview. So what do we want to achieve? So the protocol allows a group of 3 parties, P1, P2, P3, to securely compare 2 numbers, A and B, owned by P1, P2. Okay, I'm not assuming the value are shared among all 3 parties. Only 2 parties share has the private value A and B, and they want to compare which one's bigger. So the party number 3 here, just to facilitate the computation, the secure computation, right? But he or she doesn't hold anything about A and B. So the protocol going to return 1, if P to P1, P2, if A greater than B. So this is the outcome for our protocol here. Another important thing we did is called the problem transformation, right? So we transform comparison to a summation problem. We are not compare them directly. So we use a summation. We compare the sum of the bits, to make it as the same outcome as the comparison. So I can show you, what's the problem transformation we had. The first one, given two integers, right, A and B here, with L bit, domain size. We compute the alpha. Alpha is 2 times A plus 1. And then we compute the beta, right? Beta is 2 times B here. And the I denotes the most significant bit location, right? Where AI, alpha I not equal to beta I. Right? Again, that's the location we need to locate, right? If we want to compare which number is bigger or smaller. And this H here is the L plus 1 bit, binary vector, where HI is equal to 1 and HJ equal to 0, right? For the other location, right? Only one location is 1 for this H vector. Remember the H vector we compute here. So at the end, we had the H vector here. That's the same thing. Okay, so additionally, we define a couple, values here. So this is the summation we have. The S alpha, so S alpha gonna sum the individual bits of the value alpha, right? So we have the alpha, and so the S alpha is the summation, basically the number of bits, set in number represented by alpha. Right. Another one, S alpha prime. So this one is a little bit different, right? So this one is equal to HI. No, it's HJ, right? HJ minus alpha J in mod 2. So what this one gives us? Remember what's H, right? H, only one location for H has the bit 1, right? All the other are 0. So the 0 minus AJ mod 2 doesn't change anything to AJ. Okay, so 0 minus 1 give you minus 1 in the group of Z2. Under that group, you still got 1 back, right? So 0 minus anything give you the same value back, right? So 0 minus 1 give you 1. 0 minus 0 give you 0. Okay, so that's the reason we use the group 2, to do this kind of computation. So what you have here is that S alpha prime is also a summation of the set of bits after you perform this HJ, minus alpha j. I'm going to give you a little bit more information here. So here is our key observation, right? So we define the value f here. So f is equal to S alpha plus S alpha minus S alpha prime plus 1 divided by 2. So if we define this way, then f equal to 1, indicating a is greater than or equal to b. All right, and then if f equal to 0, then a gonna be less than b. Right, so this is our problem transformation. So we transform the comparison to this kind of like a summation problem, right? The S alpha prime, right? So based on these two values, we derive the comparison outcome, right? So here's why we can do that. For example, according to the definition for H and the modulo 2 operation, right? The HI minus AI mod 2 is equal to 1 minus AI. Remember, the HI is the only location that has bit 1, right? So if you do this operation, then that's what you got. The other operation, like the other location, HJ minus AJ mod 2 give you AJ. It doesn't matter what's the value for AJ, right? So what that means is that only one bit of alpha got changed, right? So if that bit is 1, you change that to 0, right? If that bit is 0 at the beginning, you change to 1. Make sense? So the difference between this S alpha prime is by 1 bit, right? So if S alpha the i's location has the 1 bit already, this subtraction here give you 1. Okay, so which means when alpha I equal to 1, right? This is implying, right, the alpha is greater than, A is greater than B, right? Because the i's location is the most significant bit location where A and B are different, right? So that's the most significant bit location, right? If that location for A is 1, clearly A is greater than B, right? So that's the observation we have. So on the other hand, right, if AI is equal to 0, then S alpha minus S alpha prime gives us -1, right? So this is the reason why here we add a +1 here, right, to make sure this number is either 0, or 1, right? Because the outcome, we want to preserve is 0 and 1, right? So 1 indicating greater than or equal to, right? 0 indicating, less than, right? So these are the two values we want to preserve. So we don't want to have any negative values. We cannot represent negative values, in the under the secret sharing schemes. So this is the transformation we have. So another, here are just highlighting, a few design principles we have. Another one, the ISO operation. Again, we need to perform the ISO operation, right? As I show you from the existing protocol, right? But the ISO operation can be done locally. You don't need any communication between the parties, right? So we can minimize the communication by, using the share in Z2 instead of share of ZP, other group, right? If we use a share on other group, then we have to communicate among the parties, right, to increase the complexity. Another thing, we want to dynamically switch groups between, Z2 and Zn, right? So to maximize the computation in Z2, right? Everything can be done in Z2. There's no communication required, right? So this is the observation we have. So group switching is done obliviously, right? You have to be careful. You don't want to leak any information when you switch the groups, through randomizations. And also, as I showed you a moment ago, right, transforming the comparison to the summation problem, right? So these are the techniques we combine, to design, much more efficient solution. Okay. So here are the high-level, summary of our yes.
So if you back up 2 steps, I think the key here, we can't learn what I is if alpha I is equal to 1.
Mm-hmm. Yeah. No.
We know that there is some alpha I that's equal to 1, but
Sure.
we don't know which I it is.
No, you don't.
That would reveal something.
That's right. You don't know. So we have to hide the I's location, right? How do we hide that? So that's part of the protocol, right? So we need to design in a way that we can hide the I's location. So I'm going to show you where to hide that I's location. You cannot tell anything.
At the end, you learn. If alpha I is equal to 1, all that tells you is that A is less than or equal to B, which is what you were going to learn anyway.
Sure. You don't know the location where they differ at the B. All right. So the steps. These are the main steps we have, right? The first we had to do input transformation, right? So I show you, the 2 times A plus 1, right? Then 2 times B. The reason being, we don't want to have equality. If we don't have equality between 2, our protocol is going to leak some information, right? So that's one thing we have to avoid. That's why we do that. And then we're going to do compute the bitwise difference. That's the ISO operator. We need to, this computation need to be done. And then the next step, we're going to locate the most significant bit difference. Then we're going to derive the S alpha prime, and at the end we're going to do a shared transformation. So these are the key steps we have. So now I'm going to go through the steps quickly here. So now you can see, right, the computation here is not symmetric, right? So the P1 going to do some computation very different than the computation done by P2. And then, P3, right? They're all performing different computation instead of everybody doing the same thing as I showed you previously, okay? So here, the P1, transform, his local value, right? I'm starting with the, again, using the previous value, A is equal to 15, B is equal to 5, right? I'm using the same example. So after you do the transformation, right, this is the value you got for alpha, right? Based on the, A and B we have. And then you compute the S alpha. Again, S alpha is just, the number of bits have been set in alpha there. Okay, so you have 5 bits here as 1, then you got 5 here. So, and the rest of the number are the random values you need to use to, when you do the group switching, you need to mask, right, the real values. So these are the values kind of serve as a mask to hide the information that could be leaked by communicating among the parties. So I'm not going into detail here, but I just show you what's the purpose of these randomized values here. For the P2, again, do input transformation, right? Double the input, and then generate the shares, right? So these are the shares of, value beta in the group of, Z2, right? So everything here, in the group of 0 and 1s. So to minimize the communication complexity. So step number 3 here, now they're gonna doing the XOR operation, right? Remember the first really important operation is the XOR, right? To compute to find out the locations where the bits are different. So here you're gonna find the E. So this is done locally. That's why I have the notation here, the PJ here, right? PJ means either party 1 or 2, right? They do the same thing here based on their own local shares, right? So no communication, whatsoever. And then this one here, the B here is the randomization. You are randomizing, so you use the RI is just 1 bit. Okay, so you're randomizing the value E here so that the party number 3, when look at the E, he won't be able to tell, right, which bit location A and B are different, right? So when we look at number 3 here, P3 need to reconstruct the real value of E here. Not the real value, but need to reconstruct the E, randomize E, right? Have been masked, the E here. So if we don't have the step B here, then the E will be leaked to P3, right? That's something we don't want. And then, so here's the group switching part, right? So now the shares, the P3 gonna generate shares in group of ZN2, right? So this is another group we use, no longer in, Z2 here. So because the subsequent computation require a bigger, share size, we can no longer use the smaller share size at the beginning to compute the XOR. So here, but if we don't do the mask here at the step 3B here, then P3 gonna learn, right? So the number of locations A and B are different, right? The bit locations. So you generate a share and then send back to the party P1, P2. And then the P1, P2 here, so J is the index for P1 and P2. So P1 and P2 gonna do the same thing here by re-randomize the value, right? Remember the E vector had been randomized at the beginning, right? Before sending to P3. So when the new share, came back from P3, then the P1, P2 gonna de-randomize the value to get the real, E1 back, E vector back. So here is the E vector here. And then I think my time is kind of running out, so I will go a little bit quicker. So you have the E vector here, and then we're going to compute this gamma vector, right? So the rest of the step is to allow us to generate the vector U here, right? This vector U here, you can look at the one location is 0, right? So that location there corresponding to the most significant bit location between A and B, where they are different. Okay, so the other location, like the X value here, is actually random values. They are not the same random value. I just want to use X to indicating they are randomized values, right? So by looking at the X value, you cannot tell anything about the actual value we're hiding. So all these computations here are done obliviously, right? So the server don't know anything about what's going on underneath the shares. Okay, but this is what happened under the shares. Okay, so again, this step number 5 is share switching again, and then the step number 7, we got back the H vector. Remember, the H vector is the one we need to transform the summations, right? So in the summations, if you remember the equation we have a HI minus alpha I, right? Hj minus alpha z, right? So that's the transformation we need. We need to get the H vector. So let me go through this, rather quickly a little bit. So I had to skip something here. So at the end, right? So the step number 9 here, we're gonna compute the, S alpha prime, right? And so this one is equal to 4, based on the the example we have. And at the end, we can derive the F value. F is the comparison outcome, right? Again, everything here is secret shared, right? You cannot tell exactly what's the comparison outcome. So the last step we have So we have one more step here, try to convert the share back to the normal computation, right? So your computation may start with a specific domain, where the share came from, right? So at the end, when we return the outcome, you also want to preserve the same consistency. Otherwise, you cannot do the subsequent, computation, right? So here, the last two steps here we have is to convert the share, back to the original domain, right? So this is the step we have here. Okay, so I will skip something here. So this is a summary of what I talk about, among these steps. It's kind of complicated here. I will share the slides with you, after the talk here. But it's the same information, but I just group all the example together to show you, how it works. So here is the table of our comparison, right? So we compare with the existing solution. The first 5 of them are the constant round, comparison protocol, secure conversion protocol. So these are the, one column representing the number of rounds required, right, to perform the secure computation. The Dunbar one requires 44 rounds, and so these are the number of bits need to be, transferred. And so, here we have like 5 rounds instead of 44 rounds, and then, we drop the leading term as well, right? So, all this protocol is bounded by, big O, L, L square, right? So L is the number of bits representing A and B. So we are able to drop that, we become, L log L. So to improve the efficiency, quite a lot. All right, and so there are some variations we are considering, at the moment. Another one, we have another version, and that trade-off, between the round and the communication complexity. We can save by 1 more round, right? So this one, the current one, is a 5 round, right? So we can reduce that to 4 round by, increasing the complexity a little bit, right? The new complexity we have is going to be L squared, big O L squared, but still the constant term is very small compared to the existing solution. So it's still very efficient. Another protocol in this table I forgot to mention is the share mine. Share mine is one of the commercial tool out there, from Europe. Their protocol is not constant round. I just want to show you what's the current state of the art, the non-constant round protocol, right? So this protocol here has, 3. So they have 2 different versions, right? The most efficient version is 3 round, plus, log 2L, right? That's their complexity. So, if you have a very small L, then, this sequential one, can be better. But if the L is big, and then, our protocol is still better, right? So we just want to see, even for the sequential one, right, the non-constant round one, where our performance compared, with them. So we also look into protocol secure against malicious adversaries, right? So the current design is only secure under the semi-honest model, right? And we expecting the party follow the protocol. So what if they don't follow the protocol, right? What should we do? So we have another version, not based on additive secret sharing. It's actually based on Samir secret sharing, right? Use some kind of commitment scheme, verifiable scheme, right, to make sure they are, kind of like secure against malicious models, malicious adversaries. All right, so I just touched a little bit. So some of the open question still out there is how do we design, verifiable secret sharing based on additive secret shares, right? So there are verifiable secret sharing scheme based on Samir, but nothing based on additive secret sharing. How do we achieve fault tolerance, right, under additive secret sharing? And then there is some new research talk about do executions, right, against malicious behaviors, right? So based on the comparison protocol, we can design more advanced protocols like privacy preserving, frank recommendations in a social network domain, some kind of sorting algorithms, query processing, and authentication tools based on comparison protocols. So if we can speed up comparison, then we can speed up these applications as well. So here are 2 of my PhD students are working on this, and this is their contribution. They cannot be here, but I need to acknowledge their effort. Without them, then I cannot be here to talk to you. Right? to maybe talk something else. But these are the existing papers we compare. And again, I think that's all I have. And sorry to take a little bit longer than I needed. But I still skip some of the technical details. So, yeah. So thank you.
We have time for a couple of quick questions. If anybody has any questions, otherwise we could take questions offline and out in the halls. If anybody has any? No?
Just wondering if you attempted to implement the protocol or like what tools you used to implement.
So we just use the GMP library. I don't know if you heard about that one. It's a big number library. It's one of the fastest out there. So it's called the GMP precision. I think number to handle large numbers. We also use the C programming language. C with GMP, they are compatible. So we use that to implement our protocols. Using Swiss server, we have the local Swiss machines locally, so we can run our protocol, in that setup.
Any others? Okay. Well, I'd like to thank you. And if you ever think it feels like it's been a long time since you've been here at Purdue, you can have this to remember that Purdue's been around a lot longer.
A lot longer than me.
Cup celebrating our 150th anniversary. And thank you for speaking at our
Thank you so much.
100th anniversary season.
Sure. Hopefully I can come back for the 200th celebration. Thank you.